Okay, super. So again, we're delighted to have Francois Arleo here to talk to us about aspects of fully coherent energy loss in proton-nucleus collisions. And Francois, when you're ready, please take it away.
Okay, I'm ready, and I'm very glad actually to be back to to South Africa in a sense with you all. And so I'm very happy also to discuss a slightly different topic as last week. So as you said, I've worked over the last, say, 10 years on something which I call fully coherent energy loss in cold nuclear matter, and this is best seen in PA collisions, and that's what I'm gonna tell you about for a little while. Okay, so here's the outline of the talk. I will first discuss briefly coherent factorization, but now in proton-nucleus collisions, and I will highlight differences from PP to PA collisions. We'll discuss the concepts of nuclear parton distribution functions, or NPDFs. And I will argue that we could expect some physics beyond this coherent factorization. And this will bring me to the second part on the energy loss in its fully coherent regime. I will present briefly the gluon spectrum, and I will discuss a little bit the differences between what I call the FCEL for fully coherent energy loss and the LPM regime that I discussed briefly last week. And then I will go to some phenomenological applications, mostly at the LHC, and we looked at different probes in PA collisions, namely quarkonium, and then from quarkonia we went to light hadrons and D mesons in a series of papers. And from the very last papers and D mesons, it's possible to in principle, use these results to reweight nuclear PDFs. I will explain what that is and why this is important. So I will show the latest results that were shown in hard probes a couple of months ago. And in the very last slide, I will briefly discuss the implications on the flux of atmospheric neutrinos. Okay, so this talk is based on a series of papers. So I will, if you're interested, I will of course let the slides, and you can click on all these references. I try to keep the flow of the talk on the spectrum and the hadron predictions, reweighting, and neutrinos. Okay, so why am I interested in PA collisions? Well, I will reduce my. Okay, now it's better. Well, because why PA? Because I think, to me at least, it's quite close to, I would say, the QCD studies in PP collisions, yet with a heavy ion flavor in a sense, because it's a simple medium that we probe, but still it's a medium, a dense medium, just like quark-gluon plasma. That's why I'm saying it looks like a bit heavy ion collisions. And but as compared to quark-gluon plasma, of course, it's not deconfined matter. It's just ordinary nuclear matter, but at least it is static. So we know it's more or less its size. We know its density profile. So it's rather sufficiently simple to master a bit quantitatively the things as compared to quark-gluon plasma, where there are so many unknowns. The measurements on the experimental side are also easier than in heavy ion collisions. You have much less underlying events, so it makes things easier. And we have lots of measurements, not only at Collider, Ecole HC, but also from fixed target experiments. So this is very interesting. Also on a very large phase space, much larger phase space than in say in the past heavy ion collisions, which are more scarce. So all this makes PA collisions quite interesting in my view. And we can formulate things to compute, say, hard QCD processes in proton-nucleus collisions, principle rather easily from PP to PA collisions. So this is the usual QCD factorization formula, which I show here now for PA collisions. Maybe you remember last week I discussed that briefly in PP, in which the cross section in PA collisions to produce a hard process with a, say, a hard scale Q is given as a convolution of parton distribution functions time the partonic cross section, which is obtained from matrix elements at short distance. So you can really compute that from first principles, and then you have to convolute that with the usual PDFs. So as for the PP collisions, the power of that factorization formula is that all these PDFs are supposed to be universal, whether you can extract them in DIS and then apply them in hadronic colliders and so on. So it's, of course, it's we cannot compute that from first principles, but at least we can get some data, and they are universal, and we know their, in principle, their evolution equation. Okay. Now the difference when going from PP to PA is just that one of these PDFs is not the PDF of the other proton, but the PDF of a nucleus. So it's quite general, and without saying what that is, the formula should hold. And there's also another difference which I highlighted here. We should not forget that this formula is an approximation. It's an approximation which should be valid when the hard scale is very, very large as compared to some hadronic scale. And this hadronic scale is not the same in PA collisions than it is in PP. So that's why I call this lambda. So it's a rather semi-hard scale of the order of 1 GeV. For a proton, I would naturally put lambda QCD, but for a nucleus, the nucleus is much bigger than a proton. So in principle, this scale is different, and quite generally should be something like what we call the saturation scale. And since it's larger, then the power corrections should be larger too. Another way to say that is that those power corrections should be enhanced in PA collisions as compared to PP. So when we compare PP and PA cross-section, we may highlight the influence of these power corrections. And so just for you to keep in mind, these will be typically the energy loss of partons in cold nuclear matter that would lead to some power corrections here. And last but not least, but since they are both in the same formula, if you don't really master that, you don't really master the nuclear PDFs, and vice versa. So, so it is important, and you will see the interaction in a sense between these nuclear PDFs, which are supposed to be universal, and these power corrections, which are non-universal. So, on quite general grounds, what to expect for FA? How does it compare to the proton PDF? So after all, you could naively say that if you think of a very super dilute nucleus, FA would just be 8 times FP. So the densities in a nucleus of anucleons is just that a superposition of a proton and neutron PDFs. And it's actually not true. That was shown in the early 80s by the EMC and NMC collaborations at CERN, and they measured structure functions in DIS on nuclei. So DIS F2 in iron target, and over that in a deuterium target, so almost like a proton. And you see these data. So back to 83, you see the data points here. In which you see that there is a 10–20% effect. So namely that if everything would scale naively as the atomic mass number of your nucleus, you would expect exactly 1. That would be, there is no modification in nuclei. But since you see it's not 1, it's above 1 and below 1, depending on the value of Bjorken X here, we conclude that there is some nuclear PDF effects. And so nuclear PDFs are more complicated than just 8 times the proton PDF. So that was 40 years ago. And now it has become really a big research field in itself on how to compute these, how to extract these nuclear PDFs. They are just in the very same way as a proton PDFs, except that the data are different. Now, instead of using DIS on a proton, we use DIS on nuclei, extracting structure functions. And all the measurements that we usually use in PP or PP bar collision for proton PDFs, we use them in proton nucleus collisions. We need to have a nucleus to obviously to constrain nuclear PDF. So this would be typically Drell-Yan, weak bosons now at the LHC, and hadrons. And I highlight hadrons here because you will see that it's these hadrons may be sensitive to other effects like energy loss effects, and that complicates the picture. Namely, these are the pions were used at RIC and demesons were used at the LHC. So there are a series of collaborations, of extractions. So the latest releases include the one from Annecy Tech back in 2015, and now there's even a very recent one, EPPS 21 from the Uvascular group, and also the latest in the field is the NNPDF collaboration, which extracted some nuclear NNPDF sets. One thing that I would like to mention here, if you go back to the formula here, you see that the nuclear PDF should be evaluated at a given momentum fraction x2 in the nucleus. So a bit naively, but still, you could conclude that all the effects, the nuclear effects that you may see in constructing, say, the ratio of PA over PP cross section, should be scaling like x2, independent of the collision energy. Whenever you know what the x2 is, it should give you the ratio of NPDFs, and therefore the ratio that you would measure experimentally. So this is called the x2 scaling, in the sense that it does not depend on these two variables in principle, but only on one variable, x2. And this you could expect. You can verify that in fancy NLO calculation, and to a very good accuracy, you would have this type of scaling behavior. Now, what to expect? So at very small x, at least, there's the physics is rather clear. There is a very high density of gluons at very small x, and at some point there should be some nonlinear evolution, which leads to shadowing or gluon saturation, depending on the theoretical framework you have in mind. And typically, shadowing or saturation would lead to suppression of hadrons. So when the density is very, very large, that's shown in that cartoon here. And this you would expect at either at very high collision energy, when whereas very, very large x2 is small, or very large forward rapidity, very large positive rapidity. X2 is proportional to, say, exponential of -y. So you could get small x2 in your nucleus at a large positive rapidity. That said, I mean, there are some frameworks like CGC to compute the strength of saturation. In the framework of NPDFs, it's just it's not computed from first principles. It's just obtained from global feeds of data. And the strength of this shadowing or saturation is poorly known, because we have almost no data at very, very small x on nuclei. Unlike the proton PDF, which is well known up to, say, 1, 2, 3% even at very small x. Unfortunately, we have much less nuclear data, and therefore we have a much larger uncertainty at small x, especially for gluons. So how to probe these nuclear PDFs? What are the best probes, best measurements that you can do? Well, I list here some, in my opinion, at least some requirements. It's not that they're all necessary, but I think they're the best requirements. Well, you want to have some large scale. You want to measure a hard process in which the Q is much larger than, say, 1 GeV, much larger than the saturation scale. And then this makes sure that factorization should be a good approximation. But you don't want either that Q squared goes to a very, very large number. Because in that very, very large number called the Bjorken limit, if you fix x, but you let Q squared and S going to infinity, then at this limit, at least the nuclear PDF should just be a superposition of proton PDFs, because you would probe very, very short distances and you would have no nuclear effect. So if you measure something with very, very large Q, it's likely that you won't have any sensitivity on nuclear PDFs. And the last point you will see clearly later, but it's to favor color neutral probes to avoid energy loss effects. If you have some color neutral probes like weak bosons or photons or Drell-Yan, then these will not be sensitive to the fully current energy loss, which I discussed. Jets, jet may be sensitive to that, but okay, Q is very, very large for jets, and it's probably also a very good way to measure nuclear PDFs. So this is, I give you some a couple of examples of data compared to the nuclear PDF extraction. So this is a nice measurement by CMS. Actually, I was proud to be part of that analysis a few years ago. So in which W is measured in P-lead collision at 80 eV. And well, this is on the y-axis, just the forward-backward asymmetry ratio as a function of the lepton rapidity. And you see the CMS data points, which have rather smaller bars, and you see the theoretical calculations. So if you ignore completely nuclear PDFs, you have this line here, and you see that it's clearly ruled out by data. But you see also two different sets of nuclear PDFs available at the time. And you see that with very, very precise data, you can favor one set or another, and maybe this set will be weighted to take into account these data. So at least you can guess that ultimately the uncertainty, the theoretical uncertainty, will converge towards the data points and towards the data uncertainty. So weak bosons are clearly very, very sensitive and very useful in order to really probe at least quark densities, because you have QQ bar goes to the W at leading order. And this was done by the global fit analysis recently. Another example which I like is this plot by the NNPDF collaboration, in which they released their latest sets. And this is done for different flavors, from the quarks and the gluons on the bottom right here, as a function of Birkenex. And just to explain, this is the blue band with that, which is very large uncertainty, say from 0.6 to 1.2. This is, again, sorry, maybe I didn't introduce that, but this is the ratio of the gluon distribution in a nucleus, in a lead nucleus, over that in a proton. This ratio is, well, something between 0.6 and 1.2. So there's a factor of 2 uncertainty here. So clearly we don't have a lot of data. So of course we don't have any constraints. And this is what is shown here when we don't use some data. And when we use some LHC data, namely D-meson projection in P-lead collisions. So these were measured by LHCb 2 or 3 years ago. Well, you see that those data are so precise and so sensitive to the gluon shadowing, to the gluon PDFs at small x, that, well, all of a sudden, if you include this data, you will have this tiny brown uncertainty here for the new set. So if you include D-meson data, wow, you have a strong reduction of your theoretical uncertainty, and you could say that, well, you really master now very precisely the amount of gluon saturation or gluon shadowing at very small x. And this I will contest at the very end of the talk. Okay. So why do I contest that a little bit? Why do I believe and I argue that actually there should be some physics beyond this collinear factorization? If there was no physics beyond that, then you could really do these global fits as was done. But we know that just looking at the data, that there should be something else. And in particular, I think of light hadron production and JSI production that was measured in PA collisions, normalized to PP collisions. So we observe a strong separation. So here, alpha is one being no suppression of JSI, no suppression of Drell-Yan, as a function of Feynman X, which is related to the rapidity, if you wish, to the longitudinal momentum of your Drell-Yan pair or JSI particle. And you see that there is a sudden drop of JSI suppression from say 0.95 to 0.7. Well, I didn't introduce alpha here, but it's a very strong suppression. So in terms of ratio, it would be something like 0.3 or so. So there is a very strong suppression of JSIs when you go towards larger and larger XF or larger and larger rapidity. You also observe some suppression in Drell-Yan, but much less. There's some effects, but there's a huge difference between Drell-Yan and JSI, and that's a bit surprising if you think about it, because of course Drell-Yan will be sensitive to anti-quarks and JSI maybe is more sensitive to gluons, but these two should be related by QCD evolution. So if it was due to gluon shadowing at small x here, you could expect something which would be much closer for Drell-Yan and for JSI. At RIC, also the production of light hadrons was measured here, I think by Brahms, as a function of rapidity above some given transverse momentum, just to ensure that it's perturbative enough. And you see a suppression here, which is quite strong, especially when you focus on the central deuteron gold collision. So you have also a very strong suppression. And why do I argue that these data show clearly a breaking of factorization is when you plot that as a function of x2. So you remember that I said that all the nuclear PDFs effects should scale with x2 independent of root S, which means that if you collect all the data that you have and you plot that as a function of x2, you should have just a single curve. You should not have, for given x2, different nuclear effects. And you see that it's not the case. You see that on the left plot, this JSI suppression data. There's a collection of data really from low energy, 20 GeV, up to 8 TeV at the LHC, and but as a function of x2. So you see the backward LHC, forward LHC, and then all the fixed target experiments. And clearly you see that it's a bit of a mess. If you focus at a given x2, I don't know, 10 to the minus 2, you have here a strong suppression at one energy and much less suppression at another energy. So it means that, okay, it depends strongly on both x2 and root S. So there is no x2 scaling. So this cannot be explained by nuclear PDFs. You can do whatever your nuclear PDF set is, you will never be able to reproduce this JSI data for sure. And the same is true for hadrons. I showed you some Brahms data before as a function of, now it's as a function of PT, and I superimposed some light hadron suppression by Alice at much larger root S, and you see that again at a given x2, you have a huge difference from one energy to another. So a very strong violation of x2 scaling. It has been known for quite a long time for JSI, but it's interesting to see that even at LHC we still see some evidence for x2 scaling violations. So clearly there is something beyond nuclear PDFs. This beyond is, at least in my opinion, that's just my point of view, but is mostly due to energy loss effects in a nucleus. So I discussed last week the energy loss of quarks and gluons in quark-gluon plasma, but you could expect the very same thing in a nucleus, because again, as I said, a nucleus is just also a dense medium of scattering centers. It's confined, but still, it's a collection of scattering centers, whether you call them nucleons or gluons inside nucleons, and there should be some multiple scattering of the high energy partons that go through the nucleus. So here, for the sketch for the cartoon, you see I show both the Drell-Yan in PA collisions and hadron production in DIS. And for Drell-Yan, the picture would be that you have an incoming, say, quark or anti-quark, if you wish, that would scatter with an anti-quark from the nucleus, and that produce the virtual photon. And doing so, they would multiply scatter in the nucleus here and emitting some gluons, therefore losing a little bit of energy before getting to the hard process. While for the DIS, it's a bit opposite. You have an incoming photon, and then there is a quark which is produced, and while going out of the medium, it will scatter, and this multiple scattering will induce gluon emission, so energy loss. Now, what's the situation for something which is not Drell-Yan, not GIS, but hadron production in PA collisions? Well, in that sense, for that observable, it looks like something a bit different, in which you have an incoming parton coming from the proton that would scatter multiply, just like Drell-Yan. And then there will be an outgoing parton in the final state, and this outgoing parton would fragment eventually into the hadron that you would measure experimentally. So it looks a bit the same, but a bit really adding Drell-Yan and DIS in the sense that you have both initial state and final state energy loss. You could have radiation here before, radiation after. And what I would call initial state is when you square this amplitude, and when you square this amplitude, you would have the final state energy loss. But you have on top of that initial and final state interference. And this is really this interference between the gluon emission, say, before the hard process, before the multiple scattering, and after the multiple scattering, that will lead to what I call fully coherent energy loss. So it's very specific to the case of hadron production in PA collisions, but as you will see, these data are very important in the context of nuclear PDF extractions. So of course, the natural question is what are the parametric dependencies on the energy loss process on, say, the energy of the parton or the medium length and so on. So on what to expect for these energy loss processes. So to answer this, we set up some theoretical setup which I want to discuss briefly here. So again, I show you this cartoon in which you have this scattering, which looks like a small angle scattering. If you think about it, maybe it's not the same pattern here than here. Here it's the same, say, a quark that would come into the nucleus and that would scatter at very small angle. Why very small angle? Because we're in the nucleus rest frame. So the longitudinal momentum is very, very large, even as compared to the transverse momentum where you would measure your particle, which may be a few GeV, but still as compared to PZ, which is very, very large, which is X times P plus, the scattering angle is very small. So the idea is that we say, suppose that we tag a hadron or a parton, if you wish, with this transverse momentum, which is much larger than what I call the saturation scale, or Q at times L square root, which is really the amount of multiple scattering, the amount of PT that this pattern gets while going through the nucleus. So what it means that in practice, we have really a hard process, which is symbolized as this hard exchange Q-perp, and this Q-perp is typically translating into this large P prime perp in the where you measure your hadron. And then on top of that, because we're in a nucleus, we have some additional multiple scattering with say n exchanges while going through the medium. And these collisions are quite exchanges are quite soft, so you can resum them. And in principle, this accumulated transverse momentum squared should be given by Q at L. And this Q at L again is much smaller than the typical hard momentum exchange here. So we have, just to summarize, we have a very hard process here, and then on top of that we add some soft rescattering. And for the calculation, we either calculated with in the first order in the opacity expansion, just computing exactly with a one additional momentum exchange, which is soft, or two all orders, just resumming here, just a bit like BDMPS in a sense. And what we verified a posteriori, but is that what matters really for this energy loss process, for this medium-induced gluon radiation, is the radiation are the diagrams in which the formation time of the gluons are very, very large. And because, well, as I will argue, when the formation time is of the order of L, then the energy loss scales like the LPM energy loss, which is independent of the energy, which is small in the high energy limit. So we can focus really on the large formation time. And so in principle, so this is the amplitude and the complex conjugate amplitude here in the reversed here. So here, this is typically a diagram in which we have an interference between the initial state radiation in the amplitude and the final state radiation in the amplitude. And then we have again this hard exchange and one soft exchange. So we already focused on these kind of diagrams to compute what we want, namely the induced gluon spectrum in that limit. And this is the result that we obtained. We obtained something which is almost independent of the energy. I mean, it depends on the log, which is very important, obviously, but something which is almost does not vary up to this log with respect to the gluon energy. So if you remember the cartoon last week for the what I call the final state energy loss of a jet in quark-gluon plasma, we had the Bethe-Heitler regime, which was like alpha S over pi. And then we had the LPM suppression when the formation time was of the order of L. And then it dropped like 1 over omega, typically, when the formation time or when the energy is large, or when the energy is much larger than the typical scale, which we called omega c q at L squared. Okay, that was what we had for the final state energy loss. So if you integrate this spectrum, you had the average energy loss, which was proportional to this scale typically. Now for fully coherent induced spectrum, because of these interferences between the initial state and the final state, and because of the long formation time integral, you can really integrate over a very, very large formation time, but we still have some non-vanishing spectrum. We have something which, as I said, I mean, varies very mildly with the gluon energy. It has some kind of plateau, a bit like the Bethe-Heitler, a bit like Guinion-Birch medium-induced spectrum, in which we have just one scattering of an asymptotic parton. And this is done over a large range of gluon energy. Here, omega hat is typically given by this ratio. So it's proportional to E times Q at L. So to it times square root of Q at L over M perp. Okay, so we integrate over all that, and then when the formation time is even larger, when the gluon energy is even larger, then we have a certain drop, like 1 over omega squared. So it doesn't really contribute at all to the pattern, to the average pattern energy loss. And physically, the radiation here is dominated by gluon emission with K perp something between the Hart scale times X. So X is the gluon energy over the pattern energy times the Hart scale Q, or M for massive particle. And it should be bounded by some the rescattering scale, which is QS. Okay, so when you have this large log integral, and then you end up just having this large logarithm in the medium-induced spectrum. Okay, so this was done first this was obtained in a model first, and then it was confirmed more a bit, say, rigorously in the opacity expansion with just one rescattering, and it should be valid at least in the soft limit when the gluon energy is much smaller than E. And this is naturally the case because the saturation scale here is always much smaller than the Hart scale Q, or transverse mass. The other, apart from that log, the other interesting thing is the color factor, and the color factor follows really from the color algebra. Well, I didn't put the formula unfortunately here as function of the traces of Gell-Mann matrices. But typically, the color factor is given by CR plus CR prime minus CT, where CR is the incoming color charge of your incoming particle, so the Casimir squared, plus the color charge of the final state particle minus the color charge of the exchanged particle. And so let's take a few examples. Suppose that you have an incoming gluon, and that will scatter in the nucleus, and that will produce an outgoing gluon that you would measure, or maybe you would measure, say, a pion or a quarkonium and so on, of course. But still, if it's a gluonic final state, then FC is just NC plus NC minus NC, because you exchange a gluon, and then the resulting color factor is NC. For quark going to a gluon, that would have the same result. You have a CF plus the gluon color charge, which is NC, minus CF, which is due to the quark exchange between the incoming particle and the nucleus. So you have another factor NC. But what is a bit funny is when you have an incoming quark that's scattered to another outgoing quark after the exchange of one gluon. Then in that case, FC is CF plus CF, so 2CF minus NC, and this is typically a negative, and given by 1 minus 1 over minus 1 over NC. And so in principle, this color factor can be negative, which is totally fine. Again, this is the induced gluon spectrum. It's really the difference between the spectrum in PA collisions minus the induced gluon spectrum in a proton. So nothing prevents it to be negative in principle. There may be less gluon radiation in a nucleus than in a proton, and that's the case in this very specific scattering channel. So all in all, when you integrate the induced gluon spectrum, you would get some average FCEL energy loss, which would scale like, so this ratio, which is a small number in principle, the QS over the hard scale. So if you remember the factorization formula, I said, oh, well, you may have some power corrections in which should scale like the hadronic scale of the medium over the hard scale. So this is typically one of such power correction to the power of 1 times the parton energy. And this is key because even though this number may be small numerically, small number, but it's multiplied by the energy. And this is, of course, in the high energy limit, this is what matters. If you remember, for the LPM, it was independent, or maybe there was a log, and we'll discuss that in the next slide. And so this proportionality has a very big consequences, as you will see later on. So just to summarize, I hope I've not lost you. So for the LPM energy loss, for what I would call the final state energy loss or the initial state energy loss, we are dominated by small formation time, meaning that all the formation time much larger than L for initial state energy loss or final state energy loss would cancel exactly between PA and PP. So what is left is gluon radiation with a formation time up to L, and this translates into this parametric dependence, maybe with a log of E, but something which depends very slowly on the parton energy, Q at L squared. Okay, and the natural place to look for these LPM energy loss is either to look on DIS on nuclei, so the EIC, for instance, or Drell-Yan in PA collisions. We final state energy loss, initial state energy loss, but also in heavy-ion collisions in which you have a particle which is certainly accelerated at very large angle as compared to the incoming particle, as compared to the beam axis. And in that case, it looks like final state energy loss. And for jets or for hadrons, you would expect for the jet quenching, you would expect LPM type of energy loss. And well, the analysis I showed last week seem to support this picture. For the fully coherent energy loss, well, this is different. This is dominated by very large formation time. But this does not vanish exactly as for the LPM energy loss, because you have the interference between the initial state and the final state. It is always sensitive to the amount of rescattering, which is symbolized by this transport coefficient here. And the parametric dependence is totally different as compared to LPM. This is, as I said, the ratio of say QS over Q over the hard scale, but it's times E. So in the high energy limit, say at the LHC, typically E is very, very large. It's the really, again, this is the energy of the parton in the nucleus force frame. So it's really gigantic. So it's much more important than LPM energy loss. That would be important, of course, for all hadron productions in PA collisions at all energies, because it really looks like the small angle scattering of a parton in going through propagating in a medium, in the nucleus medium. And we have applied this FCEL process to a series of observables to quarkonia, and we also investigated much more recently other processes like light hadrons and demesons. It needs color both in the initial and final state. Why? Well, because it's, as I mentioned briefly, it's really coming from the interference between the initial state and the final state. So if either initial or final state is color singlet, then you would have no gluon radiation, so you would have no interference. So typically there would be no effect on WZ or Drell-Yan. And this is why I said at the beginning that those data are really good to constrain PDFs, and no effect in DIS because you start with a photon. So at the AIC we should not have such FCEL energy loss, and that's good for the NPDF extraction. And as I insisted also, it's power suppressed. So typically it's suppressed by 1 power of the hard scale when the hard scale is much larger than the other natural scale, which is QS. So having set the stage for this fully coherent energy loss, having computed the medium-induced gluon spectrum, it was, of course, very tempting to go towards phenomenological applications and to see whether, even though it's predicted from first principles, to see if we see some effects in the data. So the goal that we followed mostly with Stéphane Peignet and other co-authors was to explore all the consequences on the phenomenology, but trying to be as simple as possible. Again, trying to make the least number of assumptions, trying to be simple. And well, the very first observable which we believed was interesting was quarkonium suppression, also because we had lots of data, and because it's really the production of a massive particle, so which makes things a bit easier than as compared to, say, light hadrons, in which we measure that at high PT to ensure hard process. So here, at least, it's in principle rather simple, even though we don't really master the dynamics of quarkonium production, which is complicated. But at least the picture we had in mind was that we have an incoming gluon scattering on a gluon of the nucleus, and that produce a compact QQ bar state. Okay, and we suppose that it is in a color octet state. So because it's colored, and this is colored in the initial state, we expect some FCEL effect, at least if color neutralization happens on rather long time scales. If it of course neutralizes its color very briefly, it may be different. But at least within this picture, it should be sensitive to FCEL. So with that, we constructed a very simple model, the simplest we could think of, a bit like the model I presented for the in the plasma, for jet quenching in the plasma, and namely that the differential cross section of psi particle in PA collisions. So when we take into account FCEL, would just be this very same cross section in PP with respect to the energy of the JSI, but in order to take into account the energy loss process, we have to shift from E to E plus epsilon, just to take into account this FCEL. And of course, this shift should be weighted, this shifted cross section should be weighted with a quenching weight, which is the probability distribution of this incoming gluon to lose an energy epsilon. Okay, so as I said, we don't really master the PP production cross-section of JSI. I mean, nobody really do. So since we didn't want to depend too much on the theoretical framework, we said, okay, let's just be agnostic and let's fit the PP cross-section to data. So at least this cross-section should be given by data and therefore should be reliable. And so let's do that. And this we can compute. The quenching weight can be resummed from the induced gluon spectrum. So we assume that there was a high hierarchy between all the gluon emission, because what I showed you before was the one gluon induced spectrum. So of course, in principle, there could be some multiple radiations. So a way to resum is to take this usual expression for the quenching weight, in which these gluon radiations are highly ordered in energies. So, but at least we know di over d omega because we computed it before. So we know p of epsilon, and we have then to fix a couple of say parameters. So typically the length of the nucleus, which would be given by the Glauber model. There's no real, I mean, it's rather well mastered, this part. And the transport coefficient, we don't really know, because we know it's proportional to the gluon distribution in each nucleon times the nuclear density. This is the usual old BDMPS formula. But of course, the gluon distribution, we don't really know. So, but at least at small x, it should go like a parallel. We know that from DIS. And the magnitude of Q hat, we don't really know. It's clearly non-perturbative. And so at least from a bunch of data, or either from PQCD estimates using the gluon distribution functions, we can end up having some rather good variation for this transport coefficient. That would correspond typically, just to fix the idea, to a saturation scale at the LHC amid rapidity of say between 1 and 2 GeV. So it's really in the ballpark of what could be expected. So with all this, we can compute the PA cross section, and then we can compute the RPA, which is a ratio of PA cross section over that in PP. And this was done at rate energy and compared to Phoenix data. So this is the JSI separation that was measured experimentally, and this is the typical shape that we will see many times in the, which is really coming from the from the model and from the shape of the PP cross section. So we have a clear suppression of JSIs, maybe an enhancement at very small rapidity here, and well, it really matches well the data. And the other message is that the theoretical uncertainty coming from the variation of the PP cross sections, I said we fitted it, therefore we have some parameters, we have to propagate these parameter uncertainties, and we varied also the transport coefficient from say 0.05 to 0.9, and but still doing that, we still have a rather tiny uncertainty, which is good, and which directly comes from the fact that everything is perturbative here, so we don't really have to we can master more or less the uncertainty of our model. And that at the LHC, we also predicted that before the data came, and that was for JSI and for epsilon. And the difference here, you see a much less suppression for epsilon here than for JSI. And this is directly related to the scale dependence that we predict. You remember that we had the average energy loss was proportional to square root of Q at L over the hard scale. So the hard scale would be the JSI mass here and the epsilon mass here. So the epsilon being much more massive, we expect less suppression, and this is what we predicted. And these are the Alice data. So maybe it has changed slightly, but still, I mean, it was really on top of all the data. Now it's maybe a bit below, which is good in a sense. I will discuss why. But at least the shape of almost no suppression at backward rapidity and rather strong suppression at forward rapidity is well captured by naturally captured, I would say, by the model. Even though, of course, we predict here a strong suppression. So if we had some data even slightly more forward rapidity, it would be awesome to see whether the data still follow the trend. Now, having computed JSI at different energies, I showed you these two examples, but it was also compared to many other collision energies and data. We would like to extend this model not only to JSI, but to light hadron production, because it was proposed to use light hadrons, say pions, kaons, and so on, as a way to probe nuclear PDFs. So we believe that, well, if this is a process important, if there are some data, then we have to know what the FCEL effects are. And things become more complicated here as far as the modeling goes on. Why? Because now for light hadrons, we don't have a natural large scale, which was the heavy quark mass or the JSI mass before. So the only scale that we have is to tag a hadron at large PT. Okay, so really the picture that we have in mind is that we would produce two back-to-back partons at leading order with large and of course opposite transverse momenta. So K1, K2 of the same order, much smaller, much larger than the saturation scale and the broadening scale. And of course, these two partons can carry some finite fraction psi or 1 minus psi. Okay, so instead of having, say, one particle going to one particle, we have one particle going to two particles, and this leads to several modifications. Well, we have to use a spectrum which is not derived for the one particle final state, but two particle final states. And as you will see in the next slides, in principle, these pair of patterns can be in different color representations, okay, with different probabilities. And this probability may depend on this momentum fraction here, whether there is it's very imbalanced or whether it's fairly balanced with a xi close to 1/2. Okay, so we have different color probabilities for the final state here. While before we said, oh, well, there's only color octets final state. It was easy, which had only one gluon or one octet QQ bar state. So this complicated a little bit, and then we also have some hadronization, in which for light hadrons it's a bit smaller than one, but this is not a big deal. So the model that we would have is slightly more involved, but nothing really that complicated. So now we would fix the dijet configuration. So as I showed in the previous slide, let's say here this final state is in a color representation, which I call R. Okay, and let's imagine that you measure this final state with color representation R. In principle, of course, we have confinement, we cannot really access this, but in principle, that on the partonic side, it could be measurable. So in that case, the model was the same as before. So PA cross section of that final state, which depends on psi and on a color representation R, is just the PP cross section, but with a shift. Here, the expressions are a bit different because I made a change of variable, which to make it easier at the LHC as a function of rapidity, but still it's just a shifted energy in the cross sections, and this is of course weighted by the quenching weight as before. But since the induced gluon spectrum depends on the color state of the particle, then the quenching weight does also. If you remember, I said, well, if it's the final state is color singlet, you would have no energy loss effect. So you can really guess already that the induced gluon spectrum is not the same for a singlet, which would be a delta function of epsilon, or for say an octet or a triplet or whatever final state and whatever final RR irreducible color representation. But at least for a given RR, you can have this same expression for the quenching weight, and we use the same expression for the induced gluon spectrum. And where does this R dependence on this final state comes from? Well, it comes here. It comes in this in the Casimir or the final state. And so depending on whether you have say if this is 0, then CA equals CB, and then you have 0. But if it's non-zero, well, can really be different. Whether it's if it's a gluon, then it would be NC. If it's a triplet, it would be CF, and so on. Okay. So, but if you fix R, at least you have everything, and you can compute this suppression of a color of a digest pattern. We still are a bit far away from data yet, but at least we can do this, and this should be valid. This spectrum should be valid in what we call the pond-like approximation, pond-like digest approximation, in which the two partons are very compact. So at very large PT, they would traverse in a very small distance while in the nucleus, and therefore this gluon radiation here with a transverse momentum K-perp, so with a wavelength 1 over K-perp, is much larger than the typical separation of the two particles in the final state. And actually, when you plug some the expressions for TF or the transverse velocity of these two particles, well, you end up having this large log condition, which was really the condition in which the spectrum has been computed. So there is some consistency between this leading logarithmic approximation and the fact that the gluon radiation would not see the individual parton. And this is why, in the end, we are sensitive not to the Casimir of each individual parton, but the Casimir of the full final state, just because the gluon radiation will not see the individual partons. It will not resolve that. So now, having this expression for a given R, well, what we have to do to compute a real RPA of light hadrons is, well, we need to of course integrate over Xi. We don't really know what Xi is. We integrate it over, and we have to sum over all the color probabilities rho R. Okay, for all possible rows, and then of course there is this fragmentation part, which complicates a bit the picture, but not that much. So at the end of the day, we have a slightly more involved expression, but the good thing is that this color can be computed, and this we can also guess these differential cross-sections in PP just from the data as well. So we can make some further approximation just to swap the integrals here. And at the end, even though it's approximate, the RPA of light hadrons is just the RPA of the specific configurations with color representations R as before, weighted by this the probability to be in that precisely in that color representation R. And as before, RPA of R is just given by the model which I gave before. So in principle, we can compute things. So just a few words on these color state probabilities. So of course, we have to redo the calculation for all partonic processes that we can think of. So glue goes to glue, coaglu goes to guaglu, and so on and so forth. So then now there's even some work, ongoing work of Stéphane Peignet and Kazu Watanabe and Greg Jackson, which is by the way, who's a co-author and a former student of UCT. So on the way to compute these color state probabilities and these quenching weights a bit systematically for all scattering processes. So, but here I give you this example for glue goes to glue. So a glue state can be decomposed into three possible irreducible representations. It can either be in a singlet state, or it can be an octet, or it can be in a 27-plet of a higher dimension with a higher Casimir. So the Casimir of an octet is NC, with singlet it's naturally 0. And for this 27-plet, it's almost 2 NC, so large NC. And these probabilities can be computed just looking at the projecting the amplitude on the different projectors of the different EREPs, and therefore we can play a little bit with the different expressions for the different scatterings, in which you see that for some of the scatterings here, we know that the color octet here, the final state is typically an octet here, because we have it's really projecting into the color octet state, while for the others, they can be in principle singlet and 27 plate. So just rearranging the terms from the amplitude, you can guess what are the probabilities to be in the singlet, in an octet, or in a 27 plate. And I don't go through all the details, but in principle depend on psi. And this is the result that you observe, that we compute for glue goes to glue would have different results for other channels. And you see for the singlet state, it's a 10% chance, and typically 1/NC squared, with a small dependence on psi. And for the octet and 27 plate, well, we have some probabilities of the order of 1/2 with a small dependence on psi. So at least this is known parametrically, and we can do the convolution that I explained before. So before comparing to data, then I want to show the suppression of hadrons in the glue goes to glue channel, which is just one channel. In principle, we have to sum over all the possibilities, all the possible partonic processes, but it's probably the dominant one. This is why we computed it, this one. And you again see this shape that we observed before. So just to explain, so if glue is in a singlet state, then it's singlet, so there is no gluon radiation. So RPA is 1. There's no energy loss effects. If it's in an octet state, well, it's certainly close to what I showed before for the quarkonium. And if it's in the 27 plate, because of the larger Casimir, coming from the higher dimension, we have a stronger suppression. But again, as I said, we have to perform the linear combination with the weights I showed before, and the overall suppression is shown as a dashed line. As a function of rapidity, you see it's quite close to the octet suppression. And the same is true now, not as a function of y, but as a function of pt in a given rapidity here. And you see that at very large pt, of course, when pt is much larger than qs, it should go to 1, and we have some non-negligible suppression at small pt, and again with this hierarchy of color. Okay. So. Sorry?
A quick question. I expect there are decuplets in this decomposition of glue, right?
Right. Yeah, you're right. No, in principle, but the dimension with a NC equals 3 is 0, I think, for the decuplet and anti-decuplet. So
okay,
it's proportional to NC minus 3 in a general SUNC case. And so just for NC equals 3, there is no decuplet.
That much I do remember. Okay. You say it's the 10s that are gone. Okay.
Right. Yeah, we don't have that one. But in principle, for general NC, you would have that, indeed. But yes, but really, it's fun because it's really related to the color algebra.
It's good. There are dimensional zeros in there. I just didn't really. I wasn't sure whether it was the 27 plate or the other ones. I mean, some of them.
Right. Yes. It's the 10 and 10 bar. And for the say if you. The other partonic processes are typically that we looked at was quark gluon, and that would be 3 and 6 bar and 15, as far as I remember, for the quark gluon state. And what else did we do? I mean, of course, the QQ and QQ bar with being just singlet and octet for QQ bar. So and this makes sense when you look at the suppression. It's okay. It scales a bit like the suppression would scale naturally with the Casimirs of each representation. So at the LHC now, we want to again to propagate the uncertainties and of our calculation, and this is what you see here for the different partonic processes. So there are some differences again because of the different color representations, but all in all, you see that you have always more or less the same shape as a function of rapidity. And this is shown at different rapidities, but just for different states, because of course some partonic processes would be more important at some given rapidity. Like at mid rapidity would be glue goes to glue, but at forward rapidity it would be rather quark glue goes to quark glue, because you have a dominance of quarks coming from the proton. But okay, it's just an example. So it's suppressed at very large PT, and even at 10 GeV, you see that if Y is large enough, then we even have some effects. So the message already here is that the suppression, the magnitude of the suppression is comparable to the nuclear PDFs, and you will see that maybe better for the D mesons. So here, just for the illustration, I compared to some data from Alice. So they measured the pions and kaons, and while in the model we'll have almost the same suppression for both states. And I mean, the bars are quite large, but it's roughly a good amount of suppression. At very low PT, it's not perturbative enough. So we didn't dare to extrapolate. There is no hard scale here, so we cannot do much better than that. But okay, at least the suppression is not ruled out by data. Of course, there may be some other effects, but our philosophy was just to look at this single FCEL effect and say, okay, this effect is this one. Then you can add on top other effects, obviously. And so the light hadrons was mostly discussed years ago for the extractions of PDFs, but now more and more it became clear that the D mesons should be even better. D mesons are coming from the CC bar final states, so which are very sensitive to glue goes to CC bar, even at large rapidity. And we have on top a very precise data from LHCb, which you see here on those plots as a function of rapidity at 2 different PTs. And you see that there is a strong suppression that you observe in data for D mesons at forward rapidity, and maybe enhancement at small or at large negative rapidity. But the data are very, very, very precise and strong suppression. So it is reminiscent of what we predict, except that typically the suppression that we predict is, say, 1/2, maybe a bit more than 1/2 of the suppression, which, as I said, for JSI is good in the sense that because we still believe that this is very small x2, so we may expect some saturation, we may expect some shadowing. So I'm not surprised at all that FCEL cannot reproduce everything. It's just a baseline, but maybe the suppression due to shadowing or saturation is less than what you could think of when you ignore FCEL, and I will come to that in the next slide. So this is the discussion that I wanted to have at the beginning. Well, we saw that here clearly FCEL would affect D meson production in PA collisions, and but at the same time I showed you some plots in which the NPDFs were extracting using D meson data but ignoring FCEL, because their spirit is that okay, they assume from scratch that there is exactly QCD factorization, and then okay, they can do the fit and obtain the nuclear PDFs. But of course, it's a very strong assumption, and I think we cannot ignore FCEL because it's precisely it leads to a strong suppression. So how to extract nuclear PDFs, given that there is some FCEL? It's predicted from first principles, and even though it's a model, we still believe that it leads to some important suppression. Well, as I said, well, either we use neutral probes, we use DIS, and then FCEL insensitive in this data, so it's good. But at the LHC, where you want to use these de-Mason data because they're very precise and because this is the only place in which you are sensitive to the gluons at small x, well, then you have to include one way or another FCL in the NPDF global fit. So it's really a change of way of thinking in a sense that we have to include some effects beyond QCD factorization to have some reliable NPDF global fits. And this I summarize in this slide. So you can, of course, you can ignore at all FCL, and then you would say, okay, what is the probability that I have my NPDF set given the wall data and PQCD in with say within the QCD factorization? So you can extract some good fits, and that's the result that they have. They say, okay, at least we can manage. They can manage, and it was not that easy, but at least selecting the good data that they can come up with some good NPDF sets. But you would have strong constraints. But I would say maybe results are unreliable because you ignore some things that you should not ignore, maybe. Or you can include FCL and say, okay, I have PQCD, I add FCL and I take the data, and then have another set, FA prime. So the problem is that whether you include FCL or not FCL in your analysis would result into a different set. And the problem is that the FCL strength is sufficiently large that the FA prime that they would get is very different than FA, even beyond the usual theoretical uncertainty. And that's really a worry in a sense that, well, maybe the theoretical uncertainty that you get when you ignore FCL is a bit misleading in the sense that you assume from scratch something which may not be justified. And this is another way to say it, but with a cartoon in which you have the suppression of data now as a function of PT for LHCb. And that was our prediction for FCL. It was done also with Greg Jackson and Stéphane Peignet a couple of years ago. So if this is due to FCL, then the remaining suppression is due to FA prime to the nuclear PDFs. There is some effect, but okay, not that big. If you ignore FCL, well, all the suppression from 1 to say 0.7 is due to nuclear PDF. So you see that really FA and FA prime are quite different. And this was investigated with my student Toby Avez, and he presented this plot in hard probes a couple of months ago, which I think is very interesting. So the idea was that we use JSI data as an example, and we rated the known some nuclear PDF sets which do not use de-Mason data. So this is the NN PDF3, so with a very large uncertainty because they don't use de-Mason data, which is good. And we use JSI data. So first of all, JSI are really constraining gluons. You see the two bands that we get are very narrow as compared to the to our prior for the nuclear PDFs, so which is good. Okay, these data we are not the only ones saying that. These data are really useful in constraining the gluon distributions in at small x. But if you include FCL, well, given that FCL would suppress naturally JSI suppression, well, the remaining shadowing that you have is this blue band. While if you ignore FCL and you do the weighting, then you get this band, which very looks like the band that they had for when they use de-Mason data. So it's quite consistent, this result, when they ignore FCL between JSI and de-Mason. But you see that depending on our assumption of FCL or not, you end up with two different sets. And the sets, the uncertainties of those sets is even much smaller than the distance between those two. So again, as I said, I mean, the theoretical uncertainty here does not include the fact that there may be some FCL. So it's really, I think it's really important to keep in mind that that when we use hadron production data at LHC to constrain nuclear PDFs, it's very dangerous, and unless you take into account probably this FCL effect. And sorry?
don't mind, I have a question on your error bars there. I would expect that your model for the FCEL is also, well, plagued by some error, right? I mean, it's a bit of modeling going on.
Sure.
Have you included uncertainties on this, on the error bands that you were just showing, or is this without that?
Right. No, you're totally right. So there are some parts which are easy to compute for the uncertainty, and these are shown in that band. So typically, what is most important is the value of the transport coefficient. So as I said, we varied by a factor of, say, almost 2, from 0.05 GeV squared per Fermi to 0.09. So we could have taken something even larger, but okay, this is already, we have some constraints. If we set Q hat to 0, say, of course, we would have no energy loss effects at all, and we could say, okay, then our band is gigantic. But we know that we have some sufficiently piece of data and theoretical expectations that, okay, this is quite under control. Then there is this Z momentum fraction. There is this the fitting of the PP data. So we fit the data, so it's good because we have less theoretical prejudice, but we have to propagate that, and this is the result of that band. Now, of course, there is some modeling, and there may be some systematic uncertainties that are not included in that band. I mean, the way we model things, the way we say, okay, we just shift the cross section, the expressions that we used for the quenching weight, or even the x dependence of Q hat. We say 1 over x to the power 3, and if we change that, it would affect for sure. So we could even be more conservative in a sense, and I would not say that this band with our model is the final truth for sure, because well, maybe we have underestimated some uncertainties. I tend to agree.
By looking at this blindly, right? I mean, it looks like, okay, the brown band is probably statistically induced from data. What you see in terms of errors there, assuming everything else is true and dandy. And then if I look at the blue band, it seems to be of similar size.
Indeed, yeah, and that's surprising, because in principle you would have to propagate the.
I would have expected it wrong a bit because you have an additional source of errors, but apparently.
Right. I fully agree, and actually I think we're waiting, so it's very preliminary results that was shown last month. I think that's been done just for the single say the central prediction, and it has not been propagated, so it will be slightly larger, but not more, not much, because you see that the error here is quite small. And if I may come back to the Gaussian spectrum that I showed at the very beginning here, what is interesting is that all the uncertainties, well, most except the PP cross section, but most of the uncertainty will come into that log, and we believe that this is. You see that there is Q hat, there is L, and in the end, since we are in a large logarithm, I mean, it comes in the log, and in this in the leading logarithmic approximation that we do, it's in a sense it's a bit consistent that varying these by some factors here, we may have some small uncertainty in the end, because it's precisely in the log. So it's a bit consistent that we have a rather small uncertainty, because it's just purely perturbative, except again the PP cross section. But there is some of course, I mean, in the modeling itself. So I agree with you that maybe it's slightly misleading, because it's so thin that you can say, okay, we are extremely precise. Maybe we could be more conservative, but it would not change anything in the sense that, okay, maybe the blue band would be slightly larger, But for sure, there is a big effect as compared to the no FCEL at all. Okay.
Absolutely. No, I don't think it would take away from the validity of your statement that it makes a big difference.
Yes, but there would be some work to be done to be slightly more conservative, just to be on the safe side. Yes, I tend to agree with that. And so for the very last slide, so I discovered by chance a couple of years ago that actually the D-meson production at the LHC, so we're interested in that in itself because we have some LHC data. But I found a paper in which they said that, oh, the meson is interesting in PA collisions because it has some consequences for atmospheric, the physics of cosmic ray showers. And the idea is simple. Well, suppose you have a high energy cosmic ray, typically a proton, that would collide on the atmosphere. So say something between oxygen and nitrogen. So it would develop some air shower. So it's a collection of PA collisions at the LHC in a sense. Of course, we don't really master what the initial energy is of that cosmic ray. But depending on the on your energy range, it's similar to the PA collisions at the LHC, and that's why some people want to have P oxygen collisions at the LHC, precisely because of this connection between LHC and cosmic ray physics. And what is interesting is that at high energy, of course, people try to measure all sorts of particles, but including neutrinos. And why neutrinos? Because they want to look at astrophysical neutrinos coming, say, from supernova explosions and so on. And of course, one background, or we can say it's interesting for QCD, but maybe they see it as a background, is the atmospheric neutrino coming from the decays, meloptonic decays of hadrons producing these PA collisions. And at high energy, because of the small lifetime of the D-mesons, at high energy, it would be the D-meson that would be mostly responsible for the flux of neutrinos, because the pions, the kaons have such large lifetime that at very large energy they are so boosty that of course they would decay after going through the detector. So D-mesons are in principle important, and there's many papers who computed the neutrino flux. So it depends on a complicated equation, rate equation. But it can be expressed with a simple analytic method called the Z-moment method, in which the neutrino flux follows the incoming flux of a cosmic ray times some moments of the cross section of say the proton A collision, giving the say the D-meson or the meson H in general. So the cosmic ray flux, there are several models, but just to keep in mind, it should be something like a power law, or with an E, maybe with the spectral index that would vary from say 2.7 to 3. And as I said, the moments should be directly related. It's a main convolution of the flux of the incoming cosmic ray flux times, so there's a typo here, there should be a cross section here, times the cross section of P nucleus going to H here, evaluated at a given hadron energy X, and an initial incoming incoming proton energy E over X. So it is sensitive to the cross section here. So since it's the cross section in PA collisions, it should be sensitive to, of course, nuclear PDFs as well, but FCEL too. And this is what we computed. So what we computed was to look at the modification factor R nu, so which is not measurable, but it's the ratio of the flux, neutrino flux, including FCEL over that. Sorry for the other typo, F nu with a no FCEL. So this is different than 1. And we actually show that it's just proportional to a moment of the quenching weight, where this gamma is again the spectral index of the cosmic ray flux. So we can compute this this ratio, and we see that the ratio is clearly below 1. We have some suppression as before, but now as a function of the neutrino energy here. So depending on the partonic process that produce these D mesons, because we are sensitive to the different color dynamics, we have some uncertainties here. But you see that overall, we expect a suppression, say, from 20 to 30% for what we call the conventional neutrinos, coming from the decays of light hadrons, pions, protons, and rather similar results for prompt neutrinos with coming from hadrons with a small lifetime, like D mesons, in which we are confident that it's dominated by glue, and you see this for different cosmic ray fluxes, and again the message is the same. We have a 20 to 30% suppression at high energy, so it has to be taken into account in a sense. The sizable depletion is so similar to the previous calculations using either saturation or nuclear PDF. So and it means that, well, this is the background for the astrophysical searches. Well, this background is slightly reduced by another factor of 1.2, 1.3. Okay, so this brings me to my conclusion. So FCEL is predicted from first principle with a small uncertainty, even though I agree that maybe we have to be careful with that, but at least it's a perturbative PQCD uncertainty. Let's say this way. It affects hadron production in PS. So we looked at halide hadron, D mesons, and quarkonia. It breaks explicitly QCD factorization, so it has some impact on the NPDF extractions. We have to take that into account if we use some data which are sensitive to FCEL. And the very last slide, I mentioned the neutrino fluxes and the FCEL effect. And that's all. So thank you for your attention and all the exchanges. I'm looking forward to more questions, and thank you very much.
Super. So is this the quark and plasma soup on the bottom left?
Right. Exactly. And you see some theorists who try to infer from data the nature of the soup or the FCEL. Sure. I don't know.
Super. Do we have any further questions? Let's start with Forrest.
Can you go to slide 12?
Slide 12. So, oops. Okay.
So I might have missed it, but why is there only one single hard exchange? So why do you only consider one single hard exchange?
So it's just to make it clear. So it's really the hard exchange that produces the hard process. So it's really, so if you produce a very massive particle or a very large PD particle, let's say jet, so it would be typically the momentum exchange to produce that jet. So so this is the hard process, hard exchange that we expect in PP collision. It's not it should not be confused with say the some GLV-like or single hard scattering due to the presence of the medium. It's really the if I were to draw this diagram in the usual infinite momentum frame, it would be really the propagator of the gluons producing the two, say, back-to-back jets or the massive particle. You see what I mean? So and then here the L perp can either be all soft, in which case we resum them, or they can be single hard scattering, say n=1 in the opacity expansion, as shown on that diagram. But still, even saying single hard as compared to multiple soft, but it's still very soft as compared to the hard exchange. So if you say produce a 10 GeV particle, it would not coming from, say, the rescattering, or rather soft rescattering. You see the picture. So it's a as compared to saturation picture. Usually people are interested in very low, rather low PTs of the order of saturation scale production. Here, it's really like an asymptotic pattern going through multiple exchanges. And indeed, we may have some different hard exchanges, but you would pay the price. Here, it's rather a picture of having a PP cross section and then adding on top because we really need a very Q-perp, very large as compared to QADL here, and then we supplement that with some additional rescattering. You see, it's clear.
Yeah, thanks.
Super. Next question.
So I think it was on slide 10 where you mentioned that it was quite surprising that there is some dependence on the central mass energy here. And I didn't fully understand where the assumption comes from initially that you would not expect dependence. So I understand on the y-axis here, it's just a ratio, and then is x on the x-axis, is that still just a momentum fraction? So are you essentially looking at PDFs here, and why would you initially not assume them to be different for different central mass?
Okay, so I will indeed, it was a bit fast, but if you go back to the expression, so forget about this expression here. So of course we have some convolution. So x1 and x2 are not fixed exactly. We have to integrate it over. Even though, say, if you know the mass of your particle and you have a single particle, single massive particle, just like JSI, you know that at a given rapidity, you more or less know, at least at leading order, what is x1, what is x2. You really reduce your integral. So indeed, there is some convolution, but let's say that x1 and x2, I mean, it is quite big just due to momentum conservation. So sigma PA would just be f of p x1 times f of a x2 times the cross section, okay? And you would divide that by the pp cross section. And dividing this by the pp cross section, you would, it's a bit naive and you have to do the calculation, the full calculation at NLO if you wish. But if you divide this by the pp cross section, which is what I call RPA, or alpha related to alpha in those plots. Well, the proton PDF would cancel, the hard partonic process would cancel. It's not dependent on the nucleus here. So it cancels. Of course, in practice, it's a bit more complicated because we have the sum of our IJ, we have the integrals and so on. But suppose that, say, you have glue goes to glue, and you fix x1 and x2, you totally fix your, so no more integral. It would be exact, at least. So this term would cancel, this term would cancel. So the only thing that would not cancel is FA of x2, mu, over FP, because you do PP collision, of x2. Okay, and mu is the scale of the say the J psi. So it's not, it does not depend on root S. So it leads to x2 scaling. So RPA, the ratio of P over PP, should in principle be very well mimicked by the ratio of the nuclear PDF over the proton PDF. And this ratio should be a function of x2 and mu, but mu is fixed. Okay, and so it means that whatever root S is, if there is only nuclear PDF, then at a given x2, RPA should always be the same. This is x2 scaling. It does not depend. Sorry, this is written here. RPA is not a function of x2 of root S. It's a function of x2, and then you can collect data, and you see that we are far from that. Of course, I simplified a little bit because the x2 scaling may not be exact, but at least for some hard processes which I consider, like Drell-Yan, even doing the NLO calculation and so on, there may be some very tiny x2 scaling violation because, okay, depending on the NLO processes, which may be different and so on. But to a very good approximation, if you compute the hard process with NPDFs and you divide that by pp, and you do it as a function of x2, you will see that the root S dependence will be tiny. And here you see that it's clearly not the case. Here, for given x2, you have a strong suppression at low energy and almost no suppression at LHC, and even again at 10 to the minus 2. And here you see that at RIG, typically this is a few GeV, but in terms of x2 in Brahms, it's very small because it's large rapidity. And in one case you have a strong suppression, in the other you don't have any suppression. Then things are a bit more complicated. There is coronary effect, which may not also scale like x2, but since these people, the NPDF global fits assume QCD factorization, they would expect a single curve here, and they don't use those two data because it would be impossible. So they discarded the forward hadron production at Brahms. So saying, okay, let's not use this data, but for sure they cannot reproduce. And so some people said, okay, let's use JSI. So I complain now because I say, well, if you do, then please include the other effects. But they do it at only one energy. So at one energy, there is no scaling violation because you say at one energy, but they cannot reproduce for sure this JSI suppression data, which you see the red points here are those points.
Okay, that makes sense. Thank you.
Sure.
So can you go to slide 12? Yeah.
That's
That's
a very much rough slide.
Indeed.
Yeah, I think I'm just trying to wrap my head around what this fully coherent energy loss is. So this is a gluon that's emitted before interaction with the medium, but then because of the large formation time, it's going to interact itself with the medium.
So yeah, I was quick on that. So it's good that you ask more questions. I have more time to clarify, hopefully. So again, so you see the picture with the hard process and the multiple scattering. So the nucleus is here, and in principle, well, there is the amplitude in the initial state, which you have this gluon. You have also the gluon which could rescatter on the nucleus, so with the non-abelian part. These two amplitudes are called initial state radiation at the amplitude level, and then gluon radiation, which is not shown here, in the final state. Okay. Now, okay, you sum the amplitudes, you square them, and then you are left with three pieces. So initial state radiation here, in which this is squared, and final state radiation, in which this is squared, and then the interference. If you look, say, at purely initial state energy loss here in the large formation time, so really, so we don't consider gluon radiation, say, between two scattering, it's just really large formation time, well before the hard process, well before the nucleus, or well after. This PC squared will lead to the same gluon spectrum as if there was no radiation. So the same spectrum as in PP. And so it's insensitive in the sense that, well, it could even make sense that, well, there is initial state radiation, and then, well, this parton will scatter, but whatever, I would be tempted to say, whatever, this induced, this radiation should be the same, just DGLAP-like in a sense, in PP and in PA collision. Okay, it ignores the rescattering. For the final state, maybe a bit different because you say, okay, well, there is this scattering angle, so now the final state parton has a different direction. But after all, it's the same. You have the gluon radiation, and then you integrate over all the polar angles. And this radiation at very large formation time, well after the hard process, should be the same in PP and in PA collisions. In PA collisions, it will, of course, you have gained a little bit of transverse momenta, okay? But since you integrate over all the angles, it's just a rotation here. So if you integrate over all the angles, you would have the same spectrum. So when you compute initial state energy loss and final state energy loss, really the induced gluon radiation, really the PA minus PP, The only thing that survive is when the formation time is specifically of the same order as the formation as the medium size, okay, or below as L, capital L, okay, and this survives, and this leads to LPM energy loss, which is independent of the log, independent of the energy of the parton up to some logs. So, but in the long formation time, it completely cancels. Now let me come to FCEL. Well, this is the interference part. So I said, okay, you square that, and then you have the interference. And in that case, it does, I mean, when you construct the induced spectrum, there is still some remaining finite part. And how to see that? Well, it's sensitive to the interference between the initial state and the final state. So it's sensitive to the deviation of that, say, kind of an asymptotic parton here. Okay, so there is not the same overlap between the initial state and the final state interference in PP, in which there is theta s, but there is no additional rescattering. And in PA collisions, in which, well, then there is some slightly larger rotation, so the interference term is a bit different. You see, so it's you could think of a Union-Birch spectrum in which we have just an asymptotic pattern that scatters on a single gluon, and that goes on, and you can compute that, and it leads to some pattern energy loss, which is proportional to E. But it's not a medium-induced spectrum. It's just an asymptotic pattern that experiences one scattering. And well, if you do this with a additional scattering Q perp and additional scattering Q perp plus something, then when you do the difference, you still have some surviving terms. And this is FCEL. So again, in that diagram below, in which the gluon emission is before and after, you are sensitive to the scale L perp, and this is why you have some Q hat in the end. While if you do here this curve, these gluons here, purely initial state or purely final state here, you become sensitive to L perp because you integrate over L perp in a sense. And for the initial state, well, it's even more clear, I think. You are insensitive to what happens next to that propagating parton. It's very subtle. I was a bit quick on that, so I hope it's fairly clear.
No, I think that clarifies it. Thanks.
Super. I'll ask a question from you, Herbert.
I'm good. I shot my question that you already.
Yeah. Well, can I take a prerogative of the chair?
Sure, please.
So I really like the idea of coming back to basics in the sense of thinking about energy loss in a simpler system than an AA, where things are very complicated. And you know, your mention about factorization really set off resonances in my own mind, because I feel like, you know, we've been doing energy loss for 20 years, and there's a lot of modeling. And the nice thing about factorization, which I don't know of any energy loss calculation that has real rigorous sort of Collins or Sturman or Chu type factorization proofs. The nice thing about factorization is that you really know what you're doing, as far as I can sort of tell from that community. And you have these theorems that say, okay, I'm guaranteed that any corrections are higher order, and as you wrote, you know, something perp over Q. So I guess with that as context, I wonder what you think about sort of the prospect for really rigorous factorization type proofs for these kinds of processes.
That's a good question. So I actually don't know at all whether, and in principle, I'm a bit skeptical that we can really include such process into a real factorization formula. So here I do something which is a bit hybrid. What is done rigorously, I think, is really the calculation of the medium-induced Jones spectrum. Then there is some modeling with the quenching wave, but this is still under control. And then the big step is when we do this simple rescaling. It's physical, it makes sense. I think everybody would agree that, but it does not come from first principles. So what would come from first principles is really to compute the, really the all the amplitudes with these diagrams basically, and then in which you could try to see whether there is you can really include these energy loss processes into a more general framework. So I know that Chu and Sturman and a few others, I think they derived some factorization formula at twist 4, and I remember having discussed with John Way a long time ago, and he said, yeah, in principle we can include energy losses, but I've never really seen that in practice how you would do that. So here we are left with just some modeling and it's a bit hybrid when I say, okay, let's reweight and PDF, but with something which does not really belong to the framework strictly approximation here. What is good is that where we're happy is that we have something which breaks factorization, which is non-universal. Maybe I have not insisted enough on that. It's non-universal. It really breaks factorization. But what is good is that it's power suppressed. So if it was not power suppressed, then that would be quite a shock. But here nothing prevents you, even with an n equal 1. Does not have to be necessarily 2 or even powers. So it's consistent. Again, it's within the Bjorken limit. When Q goes to infinity, we don't have any FCEL, and okay, so this approximation is valid in the Bjorken limit. Now, how to include that in the say twist 3 or 4 formalism? I know there have been some attempts by Chu and Al, but I think we are still far away from that, and at least I would be totally ignorant on how to do this in practice. So this is maybe the limit of the whole modeling here, and where we are still maybe the heavy iron touch, which I was mentioning, on which we have to model things, and which I like personally, but it's this goes a bit beyond what real practitioners of factorization would do. It's not demonstrated from first principles.
Okay, very good. Well, I think that wraps everything up on our side. I really appreciate you taking the time, and
that's great.
Taking the time to talk and then also answer all of our questions. And yeah, thank you very much.
Thanks a lot also from my end.
Thank you very much. It was a real pleasure, and hope to see you all very soon. Some places.
Real life. As real non-two-dimensional entities.
Exactly.
Yeah. Let's put in 3D. Okay.
Thank you.
Bye bye. Thank you.
Take care. Have a great weekend. Bon weekend.
Bon weekend. Salut. Bye bye.